Hi, welcome back to the series no one asked for. And in this series, like we have always been doing, I'm going to read the MapReduce paper line by line from scratch uh, without leaving any bits. So, and you're going to see what's my understanding is, and we are going to basically understand the paper in depth, like really in depth by each word. So yeah, if you haven't seen the previous parts, which I am assuming you have not, because literally no one have seen those parts. So feel free to check them out, though they are pretty lengthy and boring. But in this video, I'm going to continue from the last part I have left, which was basically the fault tolerance, I believe. Yeah, I think last time I was reading the fault tolerance portion. Yeah. I think I was reading the fault tolerance portion. And yeah, today I'm going to start with the locality. Network bandwidth is relatively scarce network in our computing environment. Yeah, we know that. In fact, according to cap theorem, like not a cap theorem, but according to extended cap theorem, we pretty much know that, not even according to cap theorem, but we know that in principle that network partition is inevitable. I'm not sure why I took a network partition example. Maybe I'm doing the system design too much nowadays. By the way, just so you know, like I have other stuff apart from research paper. That is one of the videos I'm doing right now is about system design. Like so it's a full blown series where I'm trying to design systems. Uh, and yeah, full disclaimer, I have no idea about those as well. So like I literally know nothing about system design. So yeah, it was a shameless plug, I guess. But okay, I'm going to continue. So anyways, we know that network, not network. Anyways, we know that network bandwidth is relatively scarce, and we conserve network bandwidth by taking advantage of the fact that input data managed GFS is stored on the local disk of the machine that made up cluster. Okay, GFS divides. What the hell is GFS? Wait, am I missing something? Was there some sort of GFS I'm not sure about? Okay, let's read. GFS divides each block into 64. In, GFS divide each file into 64 blocks and store several copies of block, typically three on different machines. The MapReduce master takes the location information of the input file into account and attempt to schedule a map task on machine that contains a replica of the corresponding input task. Failing that, and it attempts to schedule a map near a replica of the task input data, example on the worker machine that is on the same network switch as a large machine containing data. When a large map reduce operation on a significant fraction of the worker in cluster, most data in blah 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 blah. Okay, I did not understand a word. Like I read through the whole thing. I literally speed run, but never understood a word. Okay, so I think it will be interesting actually to see how and what they are saying. So first of all, okay, I understand that network bandwidth is a relatively scarce resource in computing environment. I'm also assuming since when this paper was written, it was around like 2005, 6, I guess 7, whenever it was written. Yeah, okay, 2004. I'm assuming that network bandwidth at that time would have been even more scarce resource, right? Okay, we did it. We understood the first line. Okay, now moving on. We conserve network bandwidth by taking advantage of the fact that input data managed by GFS. What the heck is GFS? Okay, also it says that we have it in Earth. Let me just go there. Earth. Yeah, okay. Okay, the Google files. I wouldn't have guessed. So okay, it's a file system written by Google. That makes sense. That makes sense. So now we know that what is GFS is. I think we can continue, but I'm not able to find the paper. Yeah. So for now, let's think of GFS as something like a normal file system, right? So I have basic idea of how file system works. Right? I did a basic prototyping for those, so I understand like how basic a file system works. Not sure how Google file system works. It's probably much more robust and on distributed systems. But yeah, for our purposes, I think a normal file system we are aware of should work. So we conserve the network bandwidth by taking advantage of the fact that input data is stored in local disk of the machine that make up cluster. Makes sense, makes sense. GFS divide each file into 64 mega blocks and store several copies of each. Google File System divides each file into 64 MBs blocks, okay, and store several copies of each block, typically 3 copies on different machine. Got it? So GFS is basically file system on distributed steroids. Like I think so. Yeah, I think it can be thought of like file system made by Google for distributed system on steroids. Okay. The MapReduce master take the location information of the input files into account and attempt to schedule a map task on the machine that contain a replica of the corresponding input task. Okay, so it's saying that basically MapReduce master takes the location account of the input file into account and attempts to schedule a map task on a machine that contains a replica of that corresponding input. So okay, basically what I'm thinking is they are saying that masters know the location of the input file and it attempts to schedule a map on machine that contains a replica of the corresponding input task. What I'm not understanding is why we are trying to schedule a map on a machine that contains the replica of corresponding input task. Like, why the replica? Why not why just not directly the actual machine which is containing the actual data? Like, is it because of the fact that we don't want to hinder the actual data? But that makes no sense, right? I mean, it's not like we are doing mutation on the actual data. Okay, let's see what it says. Failing that, it attempts to schedule a map near a replica of that task's input data. Okay, or maybe I'm understanding something differently now. Because if I understand, if I think like that we take the input data, okay, I think I might be able to get it, but I need to read it once. So the fact that the input data is stored on local disk of a machine that make up our clusters. Okay, so it makes sense. So like we have cluster, we have a lot of nodes, and each of those nodes will contain input data in their local disk. Makes sense, 100%. GFS divide those files into 64 MB blocks and store the copies of each of the blocks in 64. Okay, so you're saying that basically we take the input data, we take the file, distribute it into 64 MB chunks, and store them. Now it's trying to say that MapReduce master knows the location and tries to schedule a map task on the machine that contains the replica of the corresponding input data. Now this makes sense because it's clearly splitting the fact that we have a look we have input data. Google file system take that input data, chunk it out and copies it to different machines, and then master comes in and it schedules the operation map operation on these machines in which the copies was copied to, right? If that makes sense. I think that's what they are trying to say. Failing that, it attempts to schedule a map near a replica of that task's input data. Example, on a worker machine that is on the same network switch as the machine containing the data. Okay. So now if it fails to do that, it's probably just going to map it to the nearmost machine which is most suitable for to run that input data, and which is something which is on the same network, I guess. Okay, makes sense. So it's near replica of that input data, right? Makes sense. So basically what I'm understanding is saying that if it fails, it just try to see that okay, whichever is the closest to that input data, whichever machine contains that, I will just run it on that. As easy as that. And in doing that, it obviously tried to optimize for the bandwidth and all those costs. So if it's in the same network, that's the best case scenario. Okay, when running large map reduce operation on significant fraction of the cluster of okay, wait, what? When running large map reduce operations on significant fraction of workers in cluster, okay, most input data is read locally and no consume bandwidth. Okay, yeah, okay, and now I actually understand what the locality means and what was the whole point of this paragraph. So like before I summarize, I think what they're trying to say is that uh, for MapReduce to actually work, they just copying the data to copying the input data to the local disks of the workers, and then they are reading the input data, so that the actual MapReduce operation do not cost that much bandwidth. Because let's just say, if each worker have to, for each operation, for each everything, like it have to read from the network call, it will take a lot of bandwidth, because these files and these input data could be really large. So what we do is, what Google does is, it takes the input data, creates a local copy of it on the different nodes of the cluster, especially using chunking and different duplication techniques using Google file systems. And then MapReduce master comes in, it say, hey, that we have this file locally, just run map on it, right? So map task is being run on that particular copied worker in which the data was copied to. Then if it fails, like it tried to find, so hey, this is the most closest other machine we have to, in terms of the input task we had in this machine, which was just failed. So try to run it on that, and it tries to then optimize for the networks and other stuff, right? And since now we are not actually making any kind of network call, and we are reading from the uh, local disk only, it is significantly making the network bandwidth close to zero. And since it's a really significant operation which runs on very large distributed system, and a lot of workers, like trying to optimize these network bandwidth do, I believe, help Google save a lot of cost and complexity, I will say. Makes sense. hmm I mean, that was not that hard, except for the fact that I literally forgot what the paper was, and I jumped literally into locality, and I forgot what they were saying. But yeah, I think like the summary was that they are trying to consume almost no bandwidth, and that's why they are doing the initialization, copying input data to the different workers, and then they are directly reading from that workers. That was the whole summary of that paragraph. Mhm. Now we have task granularity. We subdivide the map phase into M pieces and the reduce phase into R pieces as described above. Okay, I know. Ideally, M and R should be much larger than the number of worker machines. Okay, ideally M and large should be much larger than the number of workers and machines. Okay, I think I have to read more. Having each worker perform many different tasks improves dynamic load balancing and also speed up recovery when a worker fails. The many map task it has completed can spread out across all the other workers. Okay, so I don't know what has happened. Like literally every paragraph and every line I read, I can't understand it in a single go. Like I literally have to read it 5 times to understand what it's saying, and it's pretty damn annoying. But at the same time, I can't do anything because I don't understand that. It's frustrating. It's frustrating. I mean, but what can I do? I have to read it. Otherwise, I won't understand it. Back to rereading the same paragraph, I guess. So it says that we subdivide the. Yeah, I understand that they subdivide the phases into M and R pieces. M for map and R for reduce. So that makes sense. Ideally, M and R should be larger than the number of worker machines. I think I can understand why they are trying to do that, because like if they have much larger M and R when compared to machine workers, I believe that they can probably do a lot more averaging out. What I mean is that, let's just say they have 5 workers and they have like 10, 20, 30 number of pieces. So different machine can pick different pieces, and on an average out, I think the load balancing would be pretty good, because not a uh, single worker would be overloaded. Each worker should be on average given around roughly the same amount of work. So I think load balancing should be automatically done by averaging logic, if that makes sense, I guess. Anyways, having each worker perform many different tasks improve dynamic load balancing and also speeds up the recovery when workers fail. Now the question is also it speed up the recovery when a worker fails. Why is that? Like I can understand the dynamic load balancing because if we have a small sample set and we have a lot of work to do, the likely chances of that small sample set doing an average on okay, what I'm trying to say is that let's just say we have some small sample set and we have large amount of tasks. The chance of each of the individuals in that sample set to do average amount of work when compared to other individual in the same set is pretty dang high, because uh, you obviously won't overload a single individual in that sample set, right, and leave others to do not any work. So yeah, I think the load balancing should be, or my accent just came off. Anyway, the load balancing should be pretty okay, and it should be improved because like we have such a large amount of data we want to crunch using different operations which are so large when compared to the actual workers we have to work on. So yeah, it's almost like a pigeonhole principle, right? Not a pigeonhole principle, but you get the idea, right? So if we have like a small let's just say we have m number of holes and we have m plus one number of pigeons, we know that at least one hole will contain two pigeons, right? So if we actually extend it to, let's just say we have even larger number of pigeons, we know that on an average basis pretty much each hole will pretty much contain the average amount of pigeons. Like that into like there's no, I'm not sure exactly which theorem it's called for, even if it's a real theorem or not, but that's how the intuition works, right? So that makes sense, the load balancing part, but not sure like also speeds up the recovery when a worker fails. That's something I'm not sure about, like why it speeds up the recovery when a worker fails. Not sure, actually not sure. Let's leave for now. Otherwise, I would add GPT. I would ask GPT. So these are practical bounds on how large M and R can be in our implementation, since the master must make O of M plus R scheduling decisions and keep O M into R state in memory as described above. So I think we have to deep dive into this. Not that I'm not deep diving into everything, but yeah. So master must make O M plus R decisions. That makes sense because M is the number of R tasks we have to run. Not M is the number of map tasks we have to run, and R is the number of reduced tasks we have to run. So that makes sense that we have to do O of M plus R, where O is like the big O notation. So yeah, for those of you who you bro, what, I can't even spell a word. For those of who no, for those of you, I think that's the right word, right? For those of you who don't think that data structure are used anywhere, you see, I mean, it's used somewhere, right? Somewhere. I mean, come on, somewhere. Anyway, and keep O M cross R state in memory, right? Why O M cross R? Because let's just say M is not let's just say, and since M is the number of map tasks and R is the number of reduced tasks, so technically the total state we should need to manage is the Cartesian product of M cross R, right? So we have M states in due to map operation and R state due to uh, I don't know, reduce operation. So technically the all in all state we might have to manage at the worst case is O M cross R, where O is again the big O notation. How much I'm fumbling, man. It's so annoying. It's so annoying. But at the same time it's making my English better. So I guess that annoyingness could be bearable for me, not for you guys. I understand. I'm sorry. I'm working on it. Please bear with me. The constant factors for memory usage are small, however. O of M cross R piece of state consists of approximately 1 byte of data per map task or reduced task pair. Okay, makes sense. So what they are saying is that 1 byte of data Uh, each map task or each map reduce task approximately cost 1 byte of data. So O of m cross r, even if it's due to big O notation, is not that hard, because technically it's going to be, at the worst case scenario, the maximum number would be the total number of m cross total number of r bytes. So that's is okay, I guess. That is okay even on a very large distributed systems. That is okay. Hmm. Furthermore, R is often constrained by users because the output of each reduced task ends up in separate output file. Okay, yeah, we know that. In practice, we tend to choose M so that each task individually is roughly around 16 to 64 MB of input data, so that locality optimization described above is most effective. Mm-hmm. Yeah, since because it's only 64 byte chunking, so yeah, that should be good. Also, like they said, that out R is actually constrained not only by the actual input data but also the output of each map task, which end up being as input of reduced task. So yeah, this we have read. We make R a small multiple of numbers of worker as we expect to use. Okay, we often perform MapReduce computation with m is equal to 200,000 and R is equal to 5,000 using 2,000 worker machines. Okay, that makes sense, I guess. I mean, okay. So this portion was a bit lit. I was literally scratching here and while talking. Yeah. Anyways, so this paragraph was mostly about what Google is optimizing when it comes to numbers for MapReduce. So I think we got a good glimpse of it. The only thing I'm yet confused about is why this. Like I think we read it somewhere. Yeah, it says that it also speeds up recovery when a worker fails, having each worker perform many different tasks. Why? And this is something we have to GPT it. We were reading map reduce paper and it said this. Explain. The line you're asking come from the map reduce, like Apache Hadoop. Is this the same paper? Wait, it's literally pointing to ChatGPT at chatgpt.com if you look at the leftmost bottom corner. Yeah, anyways, having each perform many different tasks improve dynamic load balancing. What does it mean? A large job split task into many small tasks. Map, reduce. We know that each instead of giving each worker one chunk of work, the system gives many small tasks over time. Yeah, not all tasks take about the same time. Some input data may be large, some data may be more complex to process, some machine may be slower. If a worker only has one large task, that task happen to be slow, it would delay the entire job. But if tasks are small, workers keep requesting new tasks as they finish, the worker automatically do more tasks. Slower worker do fewer. The system naturally balances itself. This is called dynamic load balancing. Load automatically adjusts based on the performance. Now this makes sense. Okay, so the previous explanation I gave was pretty wrong. No, not pretty wrong, but I would say not the most suitable one here. But I think this is good. That's why I like to ask GPT or GenAI. You see, here's another GenAI use. Uh, Also speeds up recovery when a worker fails. We need to know this because we didn't understand anything. If not we, I didn't understand it. You guys probably would have. If worker only had one big task, if a worker crashes near the end of the task, they hold. Oh, that makes so much sense now. Yeah, because like if we give a single worker such a big task and it fails at the end, like we have to redo the whole thing, which would take a long time. But if we give it small task, even if the progress were lost, like we can just redo the small task again. It would simply make the recovery faster. Yeah. Let's read it. Like the whole task must be redone. That could be a long time. All these small tasks that were in progress are lost. The master node simply reason those tasks to other workers. Fast recovery is fast because each task is short. Yeah. We understood it. Yeah. Makes sense. Makes sense. So 3 points says backup tasks. One of the most common causes that length the total time taken by MapReduce operation is straggler. I'm assuming straggler is a very long task. For now, let's see what it is. A machine that takes unusually long amount of time to complete one of the last few map or reduce tasks in competition. Yeah, yeah, something along the line of what I was saying. Straggler can arise for whole host of reasons. For example, a machine with a bad disk may experience frequent correctable errors that slows its performance rate from 30 Mbps to 1 Mbps. The cluster scheduling system may have scheduled other tasks on the machine, causing it to execute the map reduce code more slowly due to competition for CPU, memory, local disk, and or network bandwidth. Makes sense. A recent problem we have experienced was a bug in the machine initialization code that caused processor caches to be disabled. Crashes, not crashes, it's caches. Computation on affected machine slowed down over a factor of 100. So okay, so basically we are talking about straggler, which is a machine which is taking a lot more time that it should have to complete a single task or one of the last tasks of MapReduce. So this time we are not talking about a task which is long in general. We are talking about a machine which is taking longer time than what it should have to complete a task. We have a general mechanism to alleviate the problem of stragglers. When a map reduce operation is close to completion, the master schedules backup executions of the remaining in progress task. Okay, the master scheduler backup executions of the remaining in progress task. The task is marked as completed whenever either the primary or the backup execution completes. We have turned this mechanism so that it typically increases the computational resources used by the operation by no more than a few percent. Okay, we have tuned, not turned. We have tuned this mechanism so that it typically increases the computational resources used by the operation by no more than a few percent. We have found that this significantly reduces the time to complete large MapReduce operation. As an example, the sort program described in 15.3 takes 44% longer to complete when the backup task is disabled. Okay. So what they're basically trying to say is that to actually, you know, alleviate the symptoms of Sagler, alleviate the symptom, alleviate the what? Can't you even speak? You know, this is not actually a research paper video. It's more like me raging on my own communication skills. Anyways, so what Google does is to alleviate the problem of stragglers is that whenever a task is close to its completion, they generally master schedule backup executions of the remaining in progress tasks just to ensure that whenever the program, you know what, I'm not literally even explaining, I'm literally reading it line by line. So what's the point of me trying to act like I'm explaining? Sometimes I'm really disappointed in what I'm doing. Okay, read it once again. If you don't understand, then read it again. If you do, then explain. Don't try to, copy what is written here and try to act like you know it. And I'm not talking about you guys, I'm talking to myself. That's what I'm annoying. Okay, when a master operation is close to completion, the master schedules backup execution of the remaining in progress tasks. Okay, the task is marked as completed whenever either the primary or the backup execution complete. Okay, we have tuned this mechanism so that it typically increases the computational resources used by the operation by no more than few percent. Okay, so what it's trying to say is that, and this time I'm going to close my eyes so that I don't read it. What it's trying to say is that to alleviate the problem of straggler, what Google does is whenever a computation is closer to its completion, the master schedules all the in progress tasks into some backup, right, into some remote machines maybe, and back it up. And if those fail, they probably just run the backup machines, they run the backup task which they have scheduled. If not, If the masters just, if the main task work as good as they want, then it's okay. All in all, the task is only marked as completed when either the main or the backup execution worked. And that I think Google said that they fine tune it so that this feature does not take that much computation resources. It only takes few percent, but according to them, it does alleviate a lot of uh, significant time that MapReduce algorithm would have taken if they don't have this algorithm enabled. Oof, I did it. I did it. I actually did it. Not sure how it looked like. I will see it in post processing. What it actually looked like. Me, closing my eyes and then trying to explain it. But anyways, what I did is what I did. But it was good enough. Anyways, now we are at the fourth point, refinements, which I'm not going to read. At least not for this part. Like, I'm going to read it in just later parts. So I think this is good enough for now. I hope you enjoyed the video. Like, I don't think this video was even that much enjoyable. Why? I will tell you why. Because most of the time I was reading it, which is makes sense, which is the premise of this video. But the other times I was not reading it, I was literally raging at myself. And that's the damn annoying. And I'm still raging right now. I'm not sure why. It's it's annoying. I can't swear, but it's damn annoying. Anyways, I hope, I really hope that I'm able to actually, communicate a little bit more clearly so that at least this part of videos, not this part, but at least this portion of video get a little bit better. For now, this is, I think, one of the things I have to work upon really hard to make sure that my communications and my speaking is on par of the good. Then again, I'm not going to say I'm going to become Shakespeare, but I want to become someone who is good enough at speaking that I don't fumble words. I speak clearly. I don't do really awkward pauses, and that should be good enough for me. I think that should be good enough. Anyways, that was it for this. So we talked about basically how Google optimizes for bandwidth, that they don't do network call for input data. They store it in their local disk, and then the map and reduce operation reads from that data. So that's how they reduce the network bandwidth. And also they talk about the how they have larger number of map and reduce tasks when compared to the machines they have, so that they can do the dynamic load balancing and also ensure that there's not much risk of failure. Even if there's failure, it could be recovered really easily. Apart from that, we have also seen some usage of data structure and algorithm theory, so that's good. I am not sure like what other things is. Yeah, they also talked about some numbers that Google uses, but I'm not sure I would ever remember those. But I think that's good to know in general. Then they talked about backup, that they talked about straggler, how a machine unusually takes a long time to complete at the end moment. So it could be due to a variety of reasons, disk failure, computation sharing, or some bug. So the general mechanism is to schedule the task whichever task is being is close to completion, back it up, and only the task is marked as completed when either one of the primary or the backup task is completed. And obviously, this task is fine tuned to ensure that it does not take a lot of computation and does not share a lot of primary resources. Otherwise it would make no sense, because if the operation takes too much computation and too much hardware usage, then that would make that feature would effectively make it a straggler. Yeah, right. So that was also there. Okay, I think we are good. I will see you guys little later, and hope you enjoy. Hope you do what you are trying to do well. I'll see you later. Bye.